A very good evening to all. Myself Abhishek Danodia. माइक ऑफ है कुछ A very good evening to all. Myself Abhishek Danodia, working as a faculty in Agriculture and Soil Department of IIRS. I welcome you in this particular course and in fourth lecture of this particular defined course, where is the title defined Advanced Data Analytics for Crop Yield Estimation. Before my lecture, I think there was already 3 lectures. They give you a detailed information about crop discrimination, acreage estimation, crop yield estimation, and very first with fundamental part. So in this particular lecture, I will discuss about the advanced part, advances, where how you can use different kind of data sets, long-term data sets, big data sets, and how you can utilize for the same. So very first we start from the little background, the background which defined with respect to spectral behavior of crop or vegetation. As this particular slide give you the information about spectral informations at different wavelength, where left hand side the figure number A, figure not A define a difference between spectral reflectance in healthy and stress vegetation, which is a clear cut difference defined. Like if a healthy vegetation is there, the NIR band, near infrared band, has higher reflectance as compared to stress plant or stress crop, while in the same contradictory or just reverse to red band reflectance, a healthy plant has less reflectance while a stress plant has higher reflectance in the red band. So this crisscross you can say variation in NIR band, near infrared band, and red band ultimately used in production of various sophisticated spectral vegetation indices, and that very precisely define crop growth, crop figure as at you can say pixel by pixel variations, while right side of figure define entire wavelength of multispectral data sets from zero point 0.4 to around 2.5 micrometer. So as you can see, the vegetation, soil, water, they are spectral variations over the wavelength, and this spectral information ultimately used in generation of indices as I discussed the same. So come to the straightforward with our topic. As Patel sir in the last lecture already discussed about the crop yield estimation, fundamental part, the government schemes, and how the things was very first started in India, as well as currently how government proceed with the same. My point of concern here, like I may proceed this lecture with respect to a very first fundamental few slides, then follow up the advanced data analytics and the techniques, most specific like machine learning, integration of crop simulation model, likewise. So very first, I just brush up your memory in the part of definition, what is a crop yield estimation. So crop yield estimation defined as quantitative assessment of agriculture output, basically as we define the yield with respect to per unit area of land. It may be acre, it may be hectare, or it may be in meter square, based on biophysical with respect to biological and physical attributes of the crop, characteristics of the crop, and environment, technological factor, and that ultimately aim to forecast the crop yield or the crop yield production side on time, on before the harvesting. So which is also very much important, that not only at the time of harvesting, like currently as in the policy part, in the decision making also, crop yield forecasting before the harvest, a prior estimate is utmost requirement to give a reliable informations about expected outcome, and based on that the import export of the particular commodity can be possible with respect to their quantitative assessment on before time. And in crop yield estimations, that can be done through number of methods. We can say it ranges from the traditional conventional approach to most advanced approaches. What are the traditional approaches and what are the advanced approaches? I will discuss one by one in upcoming slides. But before that, we have to know what are the advanced data analytics advantage. Advanced data analytics, where we can use a larger number of data sets. It may be historical data sets, it may be on-time data sets, you can say real-time data sets. It may be with respect to satellite data sets. It may be because it may be from, you can say, ancillary data sets. It means not only limited data sets, a large number of data sets give you the more holistic and a scenario about the crop growth, crop condition, as well as the expected crop yield over the particular area, and where we use most advanced technology. Advanced technology where defined geospatial technology, which integrated remote sensing and GIS, GPS. Along with this, like currently, in last 1 decade, people are working the AIML, artificial intelligence and machine learning approach, and which are most favorable over the time by the various researcher, developer, scientist, and analytics persons. So now come to the part of advantage. So advantage are enlisted here, like a very less time in the processing, because once you prepare your data sets using a, you can say, big data, maybe from ancillary, maybe in situ, maybe remote sensing, and maybe from the GIS, a database layer. Once you prepare a model, set the algorithms, it may take a very less time to execute for a particular area. For a next area, just to change the same informations prior to setup in the programming format, and it may execute very much in less time. Then early forecasting using this advanced data analytics part, because although you analyze the data sets in very fair manner, so you may get the informations a prior. Before, you can say, harvesting, we can get a status, what may be the expected crop growth, expected crop yield from the same field. Large scale monitoring, because when we're talking about the remote sensing, definitely we are encountered the informations for a larger area, spatio-temporal variability over the region, and that also encounter when we're talking about the advanced data analytics, inclusion of geospatial technology, cost effective method, a very less sophisticated, you can say, instrumentations, like if I'm saying the data processor, a computer, CPU, GPU may are required. Along with this, the ground data sets or remote sensing data sets. So the cost effective part as compared to the traditional approach is quite less. Support precision agriculture, definitely it supported precision agriculture farming, where we incubate the modern technology, you can say advanced sensors like IoTs and kind of things, and also give a very realistic informations about the crop growth. Data driven policy making and real time insights. It's give you a very on time, or you can say before the harvest, crop condition or crop yield part for the same. Now come to the part of start from conventional method or the field based method, which can be used for which can be used or which are using basically by the various agriculture agencies, scholars, to get a very real time on ground information, like field based informations. Based on that, they assess what may be the crop yield from the particular field or particular area. So very first approach, like crop cutting experiment, that is the, you can say, from a longer period, last, you can say, last number of decades, researcher or agriculture agency are using that particular approach, crop cutting experiment, and where they define small a random plot of fields, they harvest it and scale the yield and estimate for a larger area, just to multiplication how much area which is covered by the same type of crops in the particular village, in the particular block, particular taluka or particular districts. Based on that, with execution of crop cutting experiment, they define how much yield may be expected for entire area specific. Then survey and farmer reports based on the ground truth information, which we call it the in situ observations and ancillary data sets, data collected from the farmer sites, and like how much area covered by the particular crop, how much the input they are used, and based on that same time, how much yield may be expected as per the previous data sets also, and with inclusion of the crop cutting, a crop yield which was already done by the farmers. So they are also add on such kind of informations based on the survey and define this is the yield of the particular field, and with add on the all sort of informations they define village level, block level and district level crop yield data. Then agrometeorological observations where based like maximum temperature, minimum temperature, maximum humidity, minimum humidity, then solar radiations, wind speed, rainfall, how much variations are there with respect to historical weather data sets, and with the same time frame what was the yield. So based on their one-to-one relationship, the statistical analysis based correlation regression, and for the statistical analysis base they define how much yield was there and in the last, and using with the particular statistical equation they use for what may be the expected yield in the next season. So with advancement of data and advanced data analytics part, or you can say approaches or technique, now AIML come into the pictures. So this a pictorial diagram which give you understanding about like what kind of different data sets are available, like multispectral data sets are available, multispectral like where RGB, NIR, red, green, blue and NIR band with along with this SWIR band, short wave infrared band. Some of the sensors may also provide the informations in hyperspectral wavelength region. Some of the cameras which directly from the data sets like visible light images they directly use, like currently people are using UAV data sets also, and where they added that advanced technology like machine learning, deep learning, and generate the information with respect to crop growth and crop behavior and yield part with comparison of in situ observations. So nowadays like the things are in advanced manner, because with respect to a realistic ground observations with integration of remote sensing and GIS, we may define pixel by pixel or field parcel by field parcel variability in the crop growth as well as in crop yield part, and that is now the time of advancement where crop yield estimation incubate that advanced data analytics part. So this is the overall list about remote sensing. I am most specific defined with respect to remote sensing only. So this is the list of remote sensing based crop yield modeling approaches. So my previous speaker already defined few of the techniques. Among them, I may discuss more you can say in advancement part, where you can say a longer or historical data sets, larger data sets can be used like in terms of phenological based yield estimation, linkage of remote sensing crop growth model and machine learning algorithms in more detailed manner. But if we enlist all sort of crop yield modeling techniques, start from the spectral yield model, like how spectral spectra behave with respect to crop growth from sowing to harvesting. So based on that spectral information, the reflectance informations and reflectance based spectral vegetation indices based informations can be used as a development of regression equations, which is named as like single date regression model, where peak vegetative crop growing period is selected, and based on that particular period specific remote sensing data sets convert in NDVI, EVI or defined spectral vegetation indices, and make a relationship with the same NDVI or vegetation indices with respect to crop yield. It may be plot level or it may be district level data sets based on the historical data sets. So once you prepare that particular regression line or regression equation, that can be used for the next year or next season to define a expected crop yield at even the mid of the season, which we define as a peak vegetative crop growing conditions. Then growth profile based model, like this was a very first Badwar model was in the same you can say align, very first they developed by Professor G.D. Badwar. They defined the growth profile model, like how that same NDVI profile may vary from sowing to harvesting, how there its increment, its you can say its peak value as amplitude, and you can say with the senescence its downfall, how it's vary over that different crop phenological stages. So that growth profile behavior also may correlate with time integrated crop conditions as well as the crop yield part. So based on that, the number of you can say equations can be developed, and which may define also the crop yield part. The second one, which is spectral meteorological yield model, where we integrate remote sensing data sets their informations may be seasonal scale or maybe multi-temporal, or you can say multi-year data sets along with these meteorological inputs. So meteorological inputs may be from the observatory side or maybe from remote sensing, or you can say satellite derived data sets also. Currently number of satellite products are also available in the geospatial world, where you can directly use satellite derived uh, output or with respect to meteorological inputs like temperature, humidity, rainfall, sunshine, dew point temperature. All sort of data sets are available at the global scale. You can directly consider as a meteorological inputs in your spectral meteorological yield model, while your spectral data sets, spectral inputs from the remote sensing data sets, and what may be your area, study area, like if your area is village level, you can use accordingly the spatial resolution data sets. Like if you are working with respect to village level, you may use the data sets of list 4 data sets, you may use the sentinel data sets. If you are working the block level or tehsil level, you may use the list 3 data sets, you may use the Landsat 8 or Landsat 9 data sets. If you are working at that district level and a group of district or maybe the state level, regional level, you may use the MODIS data sets or AVHR data sets. Likewise, number of data sets are available. Accordingly, you can prepare the model and you may use for the crop yield estimation part. In the third approach, there is a deterministic biomass production model, which is also named as the Montieth approach, which was very first developed in 1972, and where they integrate the solar radiation informations, like how much light is ultimately intercepted by the crop and how much leaf area, you can say the leaf area fraction, leaf area index is ultimately integrated with respect to how much fractional absorbed photosynthetically active radiation, which can be utilized based on the light use efficiency of the particular crop type, with integration of the scaling factor as temperature and water scalar. I think that in last lecture you although go through in detail of this particular models. In the next model, which is the phenological based yield model, where we integrate time series satellite data sets. Time series satellite data set means multi-temporal data sets for one season, and also in a replicate manner for the last 5 year, 10 year as per the data sets availability with respect to particular sensors. We may use that particular data sets, we prepare their data cube, and ultimately generate the various phenological matrices. What are the phenological matrices? How we can generate these matrices? That we will discuss in upcoming slides. Then linkage of the remote sensing and crop growth models, where you integrate the remote sensing variables with crop growth models. As crop growth models, you already have a basic idea, like crop growth model, where we integrate a location specific, site specific parameters related to the crop, related to the soil, related to weather, related to management, related to environment. So all sort of parameters ultimately define the crop growth and its behavior over the time for a multiple season. Once you parameterize your model, validate your model, then in the next season, with initial input variables, with incubation in the model, you may define what may be the crop growth over the time, expected growth. And same time with the ground observation, you can validate your models, you can say fine tuning your model and define what may be the crop growth and crop yield. But in the same, here is the beauty where you integrate remote sensing data sets. Remote sensing, which give you the spatio-temporal variability, it means the spatial informations, pixel by pixel variability. And if you integrate the remotely sensed variables, which may be indices, which may be some products, and based on remote sensing, if you generate some of the crop growth variable like LAI, leaf area index, most important, and if you incubate the LAI information crop growth model, that may definitely give a fantastic results with respect to variability in crop yield over the field scale, or you can say larger area with a fine accuracy. Then last and foremost, which is machine learning algorithm, where you may use historical yield data sets and geospatial product like visible sensor data sets and its product, land surface temperature, GPP data sets, you can say NPP and GPP, net primary productivity and gross primary productivity data sets, meteorological indices, like as I already discussed that with respect to your meteorological parameters, weather variables. If you integrate all the data sets and make it big data cubes that you can churn through the machine learning approach, there are number of techniques are there under the umbrella of the machine learning, and that may give you the more realistic informations with respect to crop growth as well as that crop yield with a finer accuracy, even with you can say using the larger data sets. So this is the overall about the number of models. Now we discuss the part of advanced data analytics with the same. So start, I just brush up your last you can say lecture memory, as well as with the advancement part, like how you can use the crop phenology and phenological based phenology derived matrices for crop yield estimation part. So like the left side of figure in this slide, as you can clear cut you can say demarcate the vegetation index and its variability with the day of year, or you can say crop season time from sowing to harvesting. So as it is with minimum vegetation indices at the time of the sowing, so there is a complete exposure of the only you can say soil part. So there is a you can say a very initial stage zero vegetation growth because of the you can say seed is already underneath the you can say soil surface. So the reflectance is only from this particular soil. So your vegetation indices value is minimum, that's why it's called a minimum vegetation indices value. So once the germination is set up, or you can say germination takes place from this particular crop type, so and the emergence come into the picture, you can say, and the seed after the emergence 2 leaf and 4 leaf stage, as you can say it's come out from the soil, that define the green up phase onset. Basically from where you can define like this is the germination, all you can say all the executed, but if I'm saying the crops also define the initial vegetative crop growing conditions. So from that up to a you can say exponential growth in the same in vegetation index as we compare with respect to time, with you can say time integrated vegetation index growth. So from that the point reach at the maturity onset, when maturity onset, when the crop is already transformed from vegetative phase to reproductive phase. So that is the point of you can say static or the stagnation in NDVI value. So as the crop varies from you can say or transform from a crop phenology stage of vegetative to reproductive phase, the NDVI becomes static, and as the you can say seed set phenological stage come into the picture, and after as the green set is ongoing, the senescence onset part is started. So the right side of the same curve define in the curve the senescence phase, which define the maturity and further senescence. And when maturity onset, when you can say grain already attained its proper size, and after the dormant phase. So this is a clear cut, a peculiar diagram of variation with respect to NDVI, but it is a standard NDVI profile of a healthy vegetation. In case of any disease vegetation or disease crop type or stress crop type, the curve may be squeezed from you can say one side, maybe left or maybe right, based on the on what time the stress may be impact on the crop, or the peak value may also be affect if the you can say the input parameter you can say the inputs which is required for the optimum crop growth may not be available for the crop growth. The right side of curve which is defined the same, if I'm saying with the crop by stage by step crop phenological stage by stage variation of paddy crop, like start from you can say from germination to its panicle initiation, then seed setting, grain filling and maturity. The same with respect to this particular curve which align on the same. So when we try to generate a phenological matrices from this spectral informations, so how you can proceed in the same? There are number of ways, like people or researchers or scientists are doing with respect to some of the sophisticated softwares are meant for that, like time set software, time set program is one of them. Then currently people are working also in the R program, R language, where they are integrate all the data cubes, you can say the area specific layer stack of all the data sets, and these data sets pixel by pixel analysis based you can get such kind of curve, like this curve as you can see in this particular slide, which is a pixel specific NDVI value over that time, is like your x-axis define time it means where 1 2 3 4 basically it is the number of scene, number of images, like very first scene what is the NDVI value on the particular pixel. So this is a one pixel specific curve, not the entire image. This is pixel by pixel variability you can encounter, and if as you have the ground truth informations, once you create like this is my optimum scale or optimum curve of phenological matrices rated particular crop type like maybe rice, maybe wheat, maybe mustard, maybe sugarcane, and based on that you may further generate the phenological matrices. What are the phenological matrices are there? They are in TimeSet software, they are as defined 14 number of phenological matrices. In our program, they are defined more than 16 plus you can say phenological matrices. But what are the important phenological matrices I enlisted here? Like very first start of the season, when your season was started for a particular crop, it means the date of sowing or date of onset in respect to you can say the germination part. So start of the season, end of the season, length of the season or the length of the growing period, peak value, peak time, base value, left small integral or you can say amplitude. These all are the important phenological matrices which has more or less significant relationship with respect to crop yield part, and which parameter that may vary with respect to crop by crop definitely. So if a crop is specific, out of these 6 or 7 or 8 phenological matrices, if 3 or 4 have the higher correlation with the crop yield part, so we may use those particular phenological matrices and generate the you can say stepwise multiple linear regression equations. And once we fit the SMLR equations, that we may use for particular crop, particular location specific. Location it means particular block level or maybe district level equation based on the crop phenology part. So in the same alignment of that, I just go through few of the our IRS projects results with alignment of the particular you can say theme or subject, so that you may get more acquainted or detailed informations about the particular methodology as well as the results part, so that how you can proceed you may get a idea about the same. Like this is one of the study which we did on the cotton crop in area of Marathwada, and which we specifically did for phenological matrices derived crop yield estimation using long-term modest data sets. So in this particular method, in this particular project, we follow this particular methodology as you can see in the particular methodology. So here, as we very first integrate all the data sets from 2011 to 2017 for the particular period specific, area specific, where we have the crop yield data sets also in the same. So we rescale, convert the data sets accordingly and make a time series of NDY data sets. Then in the time set we apply the same, you can say incubate the data sets, insert the data sets in time set software, which is basically the Photon language based software. And once we integrate that particular data sets, you can say time series of modis NDVI data sets, which is stack layer of long term period data sets. So very first we have to you can say make a curve fitting, basically just to smoothening the curve, because sometime a pixel, like if I am talking a pixel by pixel variation, so a pixel as you can say there is a clear weather conditions for a particular day. On the just next day, if there was a cloudy weather conditions, and follow with the next time which is normal, so the cloudy weather conditions may be restrict, definitely it's restrict the reflectance value from this particular area or particular locations. So your NDVI may be directly you can say go down both for the particular time specific. So just to normalize with respect to previous and successive image in between any dip or you can say peak or dip data sets, so you simply smoothen this particular curve as you can see in the same curve which is mentioned in this particular slide. So using that we can simply normalize, make a thresholding approach, and you can say smoothen the curve and generate the output image for various phenological matrices. And that phenological matrices we further generate the equations. Like this is a picture which define the spatio-temporal variability of the phenological matrices during 2011 to 2017 crop season in Marathwada region. As you can see from this particular title at the top of this particular image, the SOs define the start of the season, end of the season, length of the season, peak time, peak value, amplitude. Basically, like start of the season, end of season, length of season, that define on the day basis, while the peak time define on particular what the particular time where they can say NDVI peak value was observed in the particular area specific. And that all sort of study as we are doing here using remote sensing, it means you may get the results, you may get the output, you may get the informations pixel by pixel variability in the same. Then peak value, like on what time you may get the peak value and what was the peak value or the particular time. Then amplitude, the difference between the maximum and minimum. So all sort of information you can generate. And this is the particular curve or figure which define the year by year variability from 2011 to 2016-17 season, the interannual variations in particular type of phenological matrices, like start of the season, end of the season, to up to amplitude, year by year variation with respect to their um, you can say box plot. And the particular box plot also have the bias, you can say error, positive or negative error also, you can say based on the data variability in entire area specific. So this is also a very you can say significant informations provide, like how much variations are there with respect to a particular phenological matrices over the time, over the area, as well as their variations range in terms of entire range part. So very first, like left curve, left figure define here the correlation of you can say between crop cotton yield and the phenological matrices part. As you can see here, out of the main 6 phenological matrices, 5 phenological matrices has the high, you can say positive correlations. SOS start of the season has the negative correlation, while in out of 6, that peak value, amplitude and end of the season has highest correlation with respect to crop yield data sets. And how we can generate this particular correlation, because as we have the long term crop yield data sets at the district level, same district level, what is the after the masking, crop masking, what is the mean value of the particular parameter, like peak time, peak value, amplitude and end of the season. So their one-to-one relationship, it means district level EOS value with respect to same crop yield data sets. So likewise we prepare this particular correlation plot from the same. Then you may get also a detailed information like peak value and amplitude along with this, followed by the end of the season has highest correlation. Why it is so? So you may get an answer with the same, like peak value which define the highest NDVI value or highest NDVI pixel by pixel value, so that which define the NDVI progression during the entire season from sowing to harvesting. It means the peak value of any crop specific, you can say indices, has the highest correlation, higher side of correlation with respect to their crop yield part. Then amplitude is also the difference between maximum and minimum. So definitely it is also has a higher side of correlation, while and surprisingly that EOS end of season has the positive correlation as well as the higher side of correlation as compared to the length of the season. Why it is so in end of the season? Because as we did this particular study for cotton crop, and cotton crop has a multiple picking. So there is a more than, you can say, 2 time and 3 time picking is there in the cotton crop, cotton ball basically, to extract the cotton and lint. So in this particular crop, cotton crop, as we generate the correlation between yield versus various phenological matrices, end of the season play a pivot role just to get a, you can say, final yield assessment part. So when we prepare the stepwise linear regression equations, as you can see, where with respect to, you can say, the constant part, end of the season, peak value and amplitude are these 3 phenological matrices are included in the stepwise multiple linear regression equation. While this right side of curve define the comparison of the observed and predicted cotton yield, when we make a, you can say, using this particular equation, and we get a results of 2016 and 2017 yield prediction part. So this is the two, you can say, 1:1 scatter plot between observed versus predicted yield of the cotton crop. So which is also a significant result we found in the same area specific for cotton crop. And using that particular equations, when we generate a cotton yield map of 2016-17 and 17-18, you can see this is the map, but there is a significant variations. Why it is significant variations are there? Because that same area, one year there was normal condition, and 1 year, like in 17-18, there was the drought conditions. That's why the variability in the crop yield also encounter. And why it is so? Because you are adding the informations of phenological matrices based on multi-temporal NDVI data sets using historical, you can say, scale. So historical scale, like as you are using data sets from 2011 to 2016-17, so which is a long period data sets you are incubate here and get a more detailed information pixel by pixel variability in this your equation as well as in the final result part. Now come to the part of the advances as we're talking about the machine learning. So machine learning based regional yield crop yield modeling, where we use random forest approach in the same area of the Marathwada for the cotton crop. And we publish this work also where we integrate number of data sets. What kind of data sets, how we can proceed the data sets, what are the approach, what kind of approach we follow up, I will discuss one by one here for the same. So very first, what kind of data sets we were used in the same. So the data sets are, or you can say the variables are rainfall data sets, which is the CHIPS rainfall data sets, VCI vegetation condition index data set, which was MODIS derived data sets, then SPI standard precipitation index, which is also derived from the rainfall data sets where we use CHIPS rainfall data sets, GDD. GD is a growing degree data sets, which is we use ECMRFW data sets, which are also you can say pixelated gridded based data sets, LST land surface temperature data sets, which was derived from MODIS data sets. But how much time we integrate in terms of data? We integrate the data from June to next February, because that area in some of the locations has you can say more than 6 to 8 months for the crop production with specific cotton crop. So that's why we integrate the data sets from the June to February and define 3 different time of crop yield in terms of prediction part. So what kind of data sets we are added here? So our input data sets are SPI, VCI, GDD, LST and NSLI data sets from the ground informations. Very first we may get a correlation with respect to using random forest approach, and in the random forest approach we define what kind of you can say predictor, or you can say variables has higher you can say accuracy basic correlation. Basically we generate the predictor variable curve, and that predictor variable define which parameter has higher side of correlation with respect to crop yield data sets, and that based on that particular predictor variable we select the particular variable and generate the equations, the multiple linear regression equation, and get a 3 different time scenario like September end predictions, and December end prediction and February end predictions. We were generate 3 different equations, and these 3 equations are further utilized to generate the crop yield map also. So before getting this detail, like as when we first make a get correlation, Pearson regression you can say correlation curve with respect to different data sets like rainfall data sets, VCI data sets, SPI data sets, LST data sets and GDD data sets. So as you can see, out of this all type of input variables, VCI always has a higher side of correlation with in month of September, October, November, which is a period of very first time of picking in the cotton ball in this particular area, as we can say cotton ball picking from the cotton crop, followed by the SPI because this is a monsoon season crop. So SPI, which is derived from the rainfall data sets, has higher side of correlation as similar to just a followed by the rainfall data sets. Then GDD also has play a pivot role because GDD is the growing degree day, which is derived from your temperature data sets and which is also has the little bit higher correlation for the same. So in random forest approach, as might be if you have idea, if you may not have idea, you may get the idea from here also, like as when you want to work with respect to random forest approach, random forest basically a schematic multiple, or you can say decision tree approach, or you can say ensemble of the decision tree approach is there, as we can define it here, where we generate the OOB error for that different time period like September, December or February. OOB basically out of bag error, and which define that predictor variables and there how much variables are integrated and how much lines in terms of trees when we define its validation, the cross validation part. So the importance, you can say predictor variable and importance variables are here. You can see with respect to September, December and February, and the time with specific there like 0708 which define like July or August likewise. So these are the final equations which was prepared for September end, December end and February end. As you can see the predictor variables like RF07, the rainfall 07, it means 07 is your month. SPI 07 is the July SPI, LST 07 July LST. Likewise, as these on the basis of the predictor variable, their importance, we integrate in this particular equations and get the what may be the, you can say, their coefficient of determination and adjusted R square or adjusted coefficient of determination. As you can see, September has the highest coefficient of determination in the same case, because very first picking was there which is in bulk, and also when we compute other statistical parameter like RMSE, relative mean square error, or MAPE, which is the mean absolute percent error, or index of agreement. So September end has highest, you can say, R square, while the, you can say, least RMSE, with followed by the least mean absolute percentage error and highest index of agreement. So based on that, like you may get assess how much variations are there with respect to yield part, and as well as which time is appropriate to get the equations in expected crop yield estimation part. When we make a correlation with respect to the observed versus predicted from the same random forest approach. So as you can see, this is the particular curve as I define the figure value. This is that same scatter 1:1 scatter plot between predictor value versus observed yield in the period of the September, December and February. In the next case study, like where we integrate and we make a comparison of semi-empirical light use efficiency based model and the crop simulation model. In the, I think, previous lecture, Patel sir already discussed thoroughly about the semi-empirical light use efficiency model. My point of concern, if we compare the crop simulation model also, how much variations are there, like as we worked on that particular area. So light use efficiency, as we integrated based on the variability in the harvest index, when the harvest index may be for the cotton crop 0.07 and harvest index of the 0.12, there are variations in the crop yield part. But while when we use the crop simulation model, which is crop grow for the cotton crop specific, and as we assume the data sets at the block level in the similar based on that data sets of literature related to the crop, soil, then weather conditions and management. And so we simulate the crop yield also of 2016-17 and 15-16, but there is a large variation, it is the same. Why the large variations are there? Because as we use the data sets from the Parbhani University, their location is specific, or experimental observations for the same in the crop management part and genetic coefficients. But it has to be, you can say, specific with respect to area by area, as well as maybe you can say that block by block. Then also only you may get the higher side of accuracy as compared to your other kind of crop yield model part. Then followed by a crop yield prediction of sugarcane machine learning algorithm. As we did a mega project of SUFLAM of ISRO, where we also analyze sugarcane crop yield estimation, and in this particular project we also added or also used the machine learning algorithm for specific sugarcane crop yield estimation over a larger area, entire Uttar Pradesh. So in this particular study, like we use historical MODIS data sets, satellite data sets from the same area specific, entire Uttar Pradesh. What kind of data sets we integrate here in the same? We integrate normalized difference vegetation index and enhanced vegetation index, leaf area index, fractional absorbed photosynthetic active radiation, evapotranspiration, potential evapotranspiration, gross primary productivity and standardized precipitation index, which is a rainfall data sets. So these all data sets, very first we compose on the, you can say district wise, make a district wise average, then we make a monthly composed data sets, then we apply the regression equations. Here we applied 4 type of regression equations. And what are these 4 type of regression equations? We apply random forest regression, we apply support vector regression, support vector machine regression, then gradient boost regression, extreme gradient boost regressions, and also we estimate the yield and make a correlation also. But before that, you can say the model executions of the different, you can say, machine learning algorithm. Very first we plot the correlation of the monthly mean of the predictors with respect to their annual yield of the sugarcane crop at the which was based on the district level statistics, district level crop statistics data sets. So in this particular figure, as you can see, the x-axis represent 1 to 12 basically, which is month of January to December, while the y-axis define the correlation coefficient value. And here, as you can see, the FAPAR, fractional absorbed percent active radiation, as higher side of correlation in almost, you can say, more than 8 or 9 months, while EVI has also higher side of correlation, LAI has also higher side of correlation, NDVI also has higher side of correlation. Other parameter has moderately less or no correlation in a particular month specific. But when we integrated these, you can say, feature variables with respect to their correlation part and integrated in the machine learning approach, all defined for, which is gradient boost, extreme gradient boost, random forest, and support vector machine, that as you can see with the left side of figure, the RMSE of GBR, the gradient boost regression and extreme gradient boost equation, has the least RMSE, as well as the R square is the highest for the particular same. So this is for, you can say, model preparation and validation part also. When we define in the tabulated value, as it is like RMSE value, MSE value, mean square error, root mean square error, model absolute absolute error, and R square value. So gradient boost regression model has the higher side of R square value, and the maps of one of year, like in 2019, as we predict yield for sugarcane using the gradient boost regression. This is the map which is give you the a holistic idea, like what are the districts which has the higher side of crop yield, and what are the districts which have the you can say less and moderate side of crop yield part. So which is a very clear cut representation, like Muzaffarnagar district, Shamli district, Meerut, and then nearby the Bijnor district has the highest side of, you can say, crop yield in the sugarcane crop. And while the Bundelkhand region, the UP Uttar Pradesh Bundelkhand region, has the least crop yield prediction as the basis of the machine learning algorithm. Then this is the next study which give the more comprehensive and the holistic idea, because in this particular study, as we did for Bundelkhand region, Uttar Pradesh Bundelkhand region, but here in this particular study we compare 4 different kind of crop yield model, including machine learning algorithms, phenological matrices based yield model, then stepwise multiple linear regression model, and the weighted statistical yield model. So all 4 model, and using the historical long term data sets we incubate here and generate the crop yield model equations and their comparison also. So this study give you the more realistic and holistic idea about the same, where we did for more specifically Rabi pulses, which is you can say which are the important crops, like field pea, grams are the important crop for the same area and Bundelkhand region. So in this particular area specific, we did the study for field pea and gram, as their long term, you can say, crop statistics date records are also available. So that's why we align of that, because NC data sets also important just to make a correlation with respect to your remote sensing or geospatial technology derived products or some synthetic data sets. Very first you have to make correlation with respect to your district level crop yield data sets or maybe plot level crop yield data sets. So in this particular study, as we integrate the data sets of director of you can say agriculture, their data set which are available on our Ministry of Agriculture and Farmers Welfare website, those data sets we are added here, we were used in the same study. What kind of data sets we were used here in case of modest data sets? In case of Sentinel data set, that is the modest data, modest era, CHIPS rainfall data sets, ECMRFW of temperature minimum and maximum temperature data sets, we were used in the same study. And these data sets we ultimately integrated in generation of various spectral indices, and these spectral indices used in different kind of models. And what kind of models are there? We use here in the same, we used model of weighted statistical yield model, we used random forest regression model, we use stepwise multiple linear regression model, we use phenological matrices based treat model, and there also their comparison with respect to a crop yield data sets part. So very first start from, you can say, weighted based statistical yield model, where we define the unweighted and weighted coefficients. So the left side of this particular table define the all sort of parameters which we added here and generate their unweighted and weighted coefficients, and right side of the table of for the particular gram and field peak crops at the district level equations as we generate and their R square value. So here you can see like most of the districts has a R square value of more than 0.5 for all, with a highest is 0.89 in case of field P and 0.78 in case of gram crop for Hamirpur, and 0.89 for the Lalitpur in the field P crops. Then in case of random forest regression approach, we very first generate the variable importance curve with adding all the data sets in the random forest approach, which is basically an ensampling decision tree approach for the same gram and field P crop. In case of phenological matrices approach, we generate the particular phenological matrices like start of the season, end of the season, length of the season, amplitude and peak value for both the crops, gram and field P. We also generate the correlation, like which phenological matrices has the higher side of correlation in case of gram and in case of field P. While in case of gram, amplitude, peak value and start of the season has the higher side of correlation, while in case of field P, the amplitude and peak value, only these two phenological matrices has the higher side of correlation, and based on that particular their correlation we generate the particular stepwise linear regression equation also. But when we compare that gram and field P crop specific in all the four model, SMLR, or you can say stepwise multiple linear regression, random forest predicted, weighted statistical yield model and Penman-Montier yield model. So this is the one by one, you can say 1:1 scatter plot, left side from the gram, right side from the field P, and their variation with respect to their RMSE values also. When we compare their RMSE value with model by model, so and crop by crop, here you can see that RMSE of our weighted statistical yield model has the least RMSE value. So out of 4 model, you can say that weather variables along with this the data sets. What kind of data sets we use here? Now here you can see once again you can make an emphasis on that particular point. Like not only weather variable we incubate, but also we added some of the remote sensing derived remote sensing biophysical parameter like LST, SPI, then temperature derived GDD parameter, then their interaction also we added here, interaction and their interaction based correlation also we added in their equation formation. So here you can see the weighted statistical yield model has the least RMSE in both gram and field P crop. With the follow up, the you can say phenological matrices based yield model has the least RMSE value. So when we're talking about the crop yield estimation or crop yield prediction, weighted statistical yield model or the phenological matrices based yield model has the least RMSE or higher side of accuracy in the crop yield estimation part. So this is the inference from this particular scientific study where we compare 4 different kind of models. Now with advancement of that, like there are modern tool for early crop yield forecasting. Not only we have to added the remote sensing or GIS or GPS, but also we have to incubate, also we have to assimilate crop, or you can say crop growth model, or you can say basically the crop model as well as the climate model. So both the model has its own advantage and this its own you can say quality. Like in case of crop model give you the more realistic information in terms of crop growth with variation with respect to crop, soil, weather and management part. So it means more detailed information you can generate, and also you can simulate the behavior of the crop over the time in the particular area specific. While climate model give you the informations about based on your GCM or RCM, basically the global climate model and the regional climate model output basis, you may define what may be the expected climatic conditions or weather conditions for the same. So and same if you integrate that crop growth model information or crop model and climate model along with this remote sensing, while remote sensing has the quality of spatial variability. So spatial variability with crop growth informations with the climatic information, if you integrate all together, definitely its result is marvelous, and that marvelous result give you the more accurate in terms of crop yield prediction part, as well as to assess the crop growth over the time for the area by area, because when you're talking about the remote sensing, you are talking about pixel by pixel variability in the same. So for that, the integration of remote sensing and crop yield model is that you can say most advanced in the series of the number of models. So where remote sensing give you the information about the physiological model and overcome some of other constraint, like it may give you the information about the spatio-temporal variability, and the main advantage with the same, like it may define the actual state of plant, what may be the actual conditions, and while the crop model give you the information about the continuous description of the crop growth, the simulation also with in the next you can say 5 days, next 7 days, next fortnight scale or next month scale, expected growth defined by also in the crop model. So that it would be very significant if we conduct a study or if we integrate the data sets from the remote sensing as well as the crop growth model, and that can be give a better option with respect to crop yield prediction part as well as the regional production or productivity analysis. In the same, number of studies are although done by various developer, researcher, scientists. So this particular figure give you a pictorial version about the data, what kind of data sets are there, and how you integrate the data sets, how you assimilate the data sets at a finer scale and generate the results more detailed manner and more realistic manner with a lesser accuracy. Like remote sensing based informations, like remote sensing, it means spatio-temporal variability data sets are encountered with the same, and those data sets you ultimately assimilate through the modeling approach in the crop simulation model, crop growth model. If you integrate the in crop simulation model, where although the meteorological data sets are there, crop data sets are there, soil informations are there, and management data sets are there in terms of their fertilizer and nutrient and other you can say other package and practices. So once you integrate the data set, the data assimilation is there, you can generate the informations and more precisely, and also pixel by pixel, field by field variability you can define. Like here in right side of curve in the same pictorial diagram, define the LAI variability from all the phenological stages, from sowing, from seedling to jointing, heading, flowering, filling and maturity stage, while the variation with respect to crop models simulation curve or data simulation curve. So when you simulate the data assimilation simulation curve has little bit higher side of LAI. Why it is so higher side of LAI? Because it may give the realistic informations with the same. They are not any kind of you can say distortion or you can say error integration in the same computation part. So there are number of studies are done, like this is one of the study which was done in India in form of IRI as well as their research center, where they integrate the data sets of the satellite as well as using some modeling approach, radio transfer equation modeling approach, generate some of that parameters like LAI, and that LAI assimilated data sets is further integrated in the crop you can say info crop growth simulation model, and based on that they forecast the phenology, yield and data sets and total dry matter map also. So this is one of the results of that particular project. In this particular project, where they generate the maps of the simulated grain yield of 2015-16 and 16-17, where they integrate the actual weather conditions as well as the forecasted weather with respect to progressive LAI assimilation as they generate from this data assimilation part in the modeling approach, in the programming approach. So such kind of results are also give you the more enlightening as well as that field by field variability with a very realistic manner, less RMSE and higher side accuracy in terms of modeling approach. So integration of remote sensing with respect to crop growth model is a current time you can say advancement, where we may get more realistic information with a spatio-temporal part also. Come to the part of government side. What are the government schemes are there which is responsible with the same, like Pradhan Mantri Fasal Bima Yojana. And in the Pradhan Mantri Fasal Bima Yojana, under that particular, there is a ambitious program was started, the Yes Tech program. You may get the details of the Yes Tech manual of 2023 also. The details are there in MNCFC and Pradhan Mantri Fasal Bima Yojana, and their portals are also. What are the models are there? Basically, Yes Tech program is the yield estimation technique, which is the acronyms of the yield estimation technique. And what kind of models are, what type of models are there? So there are total 5 type of models as they are used from the various you can say agricultural agency, as they are estimating crop yield for the major crops as well as the minor crops, to define a field by field variability, but integrations of advancement in data analytics part. How it is? Like very first they integrated the geospatial technology. When we're talking about the remote sensing GIS, in each and every model where they integrate the information of remote sensing and the ground informations. Ground information they try to add as a limited manner, so that without you can say a more field oriented, or you can say ground sampling oriented model they may prepare, and they generate the results of the crop yield, and that crop yield prediction, and that crop yield prediction is ultimately utilized in crop insurance scheme of the government of India. So what are the 5 models are there? The 5 models are enlisted here, which we although discuss in our previous last lecture and our this today's lecture. The semi-physical model, which is more or less you can say the similar, your light use efficiency model, the Montieth approach. Then AI/ML models, artificial intelligence and machine learning based model, as we discussed today. Crop simulation model, the number of crop simulation model are there, like DSET models, InfoCrop, WAPOST, Aquacrop. Number of models are there which are used for the location specific or field specific crop simulation or crop growth in a simulated manner also. Then ensemble model, where they integrated the crop simulation, semi-physical or artificial intelligence. Ensemble, it means more than 2 type of model they prepare, and with integration of them, ensembling products they may generate with respect to crop yield prediction part. Then parametric index for the crop performance, where you can say based on remote sensing or with integration of ground information, ancillary data sets, there may formation or development of new indices, which may be the growth indices, or which may be some scaled indices, and that scale indices may use as an indirect approach, may use for crop growth and crop yield prediction part also. So these all are the 5 models under the Yes Tech program. What are the future prospects for the same? So definitely geospatial technology with advanced data analytics play a influential role in agriculture sector by increasing yield, managing the resources, prediction of outcome, and improving the farm practices. So with the same, like as we are talking about currently AI/ML technique, crop simulation model, crop growth model, integration. So definitely they may solve all sort of problems in a very realistic manner. So with the use of remote sensing, GIS, AI/ML and data analytics, farmer can be able to understand site specific needs for their farm as well as the expected yield from this farm. Then researcher and developer are capable to implementing crop yield estimation technique that will ensure the yield estimation in well advance with a prior you can say period, as well as, if I am saying well in advance, as well as with a lesser accuracy. So the precise crop estimate will be useful for the various government scheme like Pradhan Mantri Fasal Bima Yojana, Pradhan Mantri Fasal Sinchai Yojana, Yes Tech program and their upcoming projects also. So this is overall about that particular lecture, and how we can see a future farms which is small and smart, where all sort of new techniques, data analytics or instrumentation are used with improvement in the assessment and the estimation of the crop growth and crop yield part. And when we are talking about this future farms, as we are talking about the family doctor, so hopefully in the next couple of year or next 5 year, there may be a term come into the picture which make or which can be say as a family farmer. What is the family farmer? Family farmer, like as we are dependent on various our, you can say, daily, you can say, our food and other material like milk also, grain also, vegetables also, all sort of, you can say, our food materials has to come from a particular farm only, which is you can say clean in terms of its production, which maybe you can say healthy, healthy in terms of its production, which may be chemical free in terms of its production. So as we are talking about the family doctor, so hopefully in upcoming time there may be chance of family farmers come into the picture, and where these advanced technologies are utmost used to define the crop condition, crop growth, or the crop yield in well in advance. So thank you very much from my side. This is all for this particular lecture. If you have any query, you may please write in the chat box, or you may just message us. Thank you. Thank you very much. Okay, so welcome back in question answer session. So I just may take up questions as various our student or our scholar may ask the questions related to particular lecture specifically. So I just call up the questions and follow by the answer. Like a question was asked as how does the Montieth model use solar radiation and leaf area for the yield estimation? Basically, in the Montieth model, they integrate the informations of how much light is utilized by the crop. So, in that they use FAPR, fractional absorbed photosynthetic active radiation value, multiplying with the light use efficiency, the maximum scale, as well as for multiply with the scalar value. The scalar value is the temperature scalar as well as the water scalar, because temperature and water are the two controlling parameter, or you can say the factor which affect or impact on the crop yield part. So, in that they integrate that particular equation. So, that is the same as I think Patel sir discussed in lecture also, and today I also briefly define that particular method. The next question is how do you effectively address data sparsity and heterogeneity when combined ground truth yield data with high dimension geospatial data like drone imagery, sensor network and weather models. Okay. Basically, when you want to work with respect to crop yield model, and crop yield model, in what kind of model you have to use, that you very first define. Like in case of spectral meteorological yield model, you may generate the data sets or you may generate the model. Like very first you have to prepare the data sets. For the preparing the data sets, as you download the historical or the long term data sets of particular parameter like temperature or rainfall data sets, humidity data sets, then NDVI, EVI or LST data sets, or or you can say they are derived parameters, any of the derived parameters. If your crop yield or ground observation data sets as the field, what may be, like it may be field parcel level or it may be at district level. If you are working at the regional scale, so your data sets you should prepare as the district scale. Like you are working on a district A, so that what is the yield of A, that is your Y, and what are the x1, x2, x3, which is your independent variable, which are basically the district level mean value of the particular variable. Like it may be the temperature, it may be the humidity, it may be the solar radiation, it may be that NDVI, EVI, LST, what may be the variables you are taken up. Accordingly, you have to prepare the particular table. Then you apply in like what kind of statistical equations you are may prepare, like MLR, SMLR, or maybe further machine learning based approach like a random forest, SVM, or anyone, ANN, anyone. Like the next question is how are machine learning algorithm applied in the crop yield modeling using remote sensing and meteorological data sets. So remotes, basically you have to prepare the remote sensing and meteorological data sets with align your crop yield data sets, same as I discussed. And once you prepare that you can say the database, then you can use maybe the programming platform, you may use the R program, you may use that their defined tool also, which are added in number of the softwares like GIS based softwares also. You may use those kind of tools for the calculation part. The next question is among MODIS product like NDVI, LAI, FPAR, GPP, which are the most relevant for the crop yield modeling and why? Basically it is based on like what kind of crop you are choosing and what is the relationship between or correlation between the crop, the particular crop yield and that variable like the FFR, LAI, GPP or NDVI value. That's dependent on that, not the fix with the with respect to area or with not the fix with respect to crop. Okay, one question like explain about LAI, FPAR and GPP. LAI basically the leaf area index. Leaf area index in a simple word, it is a ratio of leaf area index is a ratio of leaf area divided by ground area. So your leaf area like if you want to compute the leaf area index. So just to make example, just say area, take a or select a area 1 by 1 meter square in length on width basis in the field. You simply cut down the all the you can say leaf or you can say near to the soil surface or plant near to the soil surface. Then place all the leaf on the ground. Okay, if the ground is fill up and the same 1 by 1 meter area is completely covered up by the leaf 2 times. So leaf area is your 2 meter square and your ground area is 1 meter square. So now your LA index value is 2. If it is, if that same ground is filled only 1.5 time. So 1.5 divided by 1 it is 1.5. So your LAI value, leaf area index value is 1.5. So that is a very basic thing. Currently for LAI estimation or LAI measurement, there are number of sophisticated instrumentations are there. Like we call it as a plant canopy analyzer. So number of companies are designing, they already selling their products in the instrumentation like Lycor companies are there, Delta T companies are there, then LPAT, the Acupar, the Decagon device companies are there. Number of companies are there, those FOGs are there, number of companies are there in the market. Like those who are preparing, although selling their products or instrumentation, name the plant canopy analyzer. Like Biogeoscience also one of the company. So number of companies are there like in the same. And using that particular instrumentation. Now why we are using instrumentation? Because instrumentations is has a upper hand in terms of, because you need not to cut the plant. You should not cut the plant without cutting. You can say a non-destructive method is there when you use plant canopy analyzer for measurement of LAI. So every time, like whenever you want to measure that LAI, no need to cut that particular plant. Simply you can say use the particular instrumentation and measure what is the LAI. And why the LAI? LAI is a important or crucial parameters which define the crop growth and has a more you can say quality relationship with respect to crop yield part and its biomass. Come to the part of the next what is LAI, then as they ask about FFR is the fractional absorbed photosynthetic active radiation, which is basically define how much leaf area is there, which is the fraction of leaf area, which ultimately used to absorb the photosynthetic active radiation value, the how much light is lying on the crop surface canopy area, and how much fraction is absorbed by the particular leaf. That is the FFR. GP is the gross primary productivity. Basically, it's define how much you can say a biomass can be produced or may produce by the particular crop or vegetation utilizing the sunlight, water, CO2, all the resources. So that is the GPP. The next question, for crop simulation versus data assimilation, like what are the critical decision criteria for choosing between a standalone crop simulation model and a data assimilation framework for the regional estimation? Definitely, very first you have to make that part of data assimilation. You have to prepare the data sets accordingly. Then data assimilation, with a gridded size, because in case of your crop simulation model, always it is working on a field scale experimental side or location basis, a point scale basically. But in case of your when you integrate the crop or you can say the crop model with respect to remote sensing, now you have to generate the results pixel by pixel variability. So very first and important is the part of the data assimilation. There is a number of data assimilation techniques are there. If you just go through like the same, you may get that you may detail about the data assimilation as well as the further integration with respect to you can say crop simulation model. Next question is like, which month has the highest influence on the final crop yield? It is dependent on the what kind of seasons you are selecting. Mainly a period of when the crop has its maximum crop growth, or you can say peak vegetative crop growing condition followed by the reproductive phase. That period or that time is the always has the higher correlation with respect to crop yield part. So that period, not in terms of specific, if I am saying, in case of your Kharif season, mostly we can say August and September. In case of Rabi season, it's Feb and March month is most appropriate for the same, mostly for the crops, not specific with a particular crop type. There is a question, can we use ensemble models like stacking or blending to improve the accuracy of crop yield estimation across heterogeneous region? Very first you have to parameterize your input parameters, then perform the statistical analysis, then you can perform that part of ensemble. Ensemble can only be possible if you have a similar kind of results, otherwise ensemble may not give a accurate results in case of you can say even crop yield modeling part also. Okay, there is a next question for hybrid yield model like machine learning plus crop growth physics. How can we balance data driven accuracy with interpretability for farmers, especially when scaling across diverse agroclimatic zone? So for that, very first when you prepare the model, you have to strict with respect to your model development in each and defined agroclimatic zone, because as the changing in the agroclimatic zone, the meteorological conditions, that biophysical condition, and as well as the important crop, the you can say predominant crop, the area may also be changed. So very first you have to define with respect to if make comparison in the agroclimatic zone basis. So zone by zone you have to parameterize, you may perform the model, maybe integration of the machine learning and crop growth model, and then may provide the advisory or maybe you can say solution to the farmers also. There is one question, what are the best practice for the selecting and weighing that indices for optimize the performance of the model, and how do we avoid redundancy in issues? Redundancy issue, basically it is like how you can define what parameters are appropriate for you, what are the variables is appropriate for you. For that, no need to worry. Very first you have to perform the correlation with respect to your, you can say your crop yield versus your input variable. Those variables which has the higher side of accuracy, but also check it out is this variable is completely independent or not. For that you have to make a calculation of multi-collinearity test. So, multi-collinearity test define like is that any data redundancy is there or not. So, multi-collinearity or VIF test or VIF you can say analysis may give you the particular solution or answer for the same. Then what is the importance of the ground truth data in validating remote sensing model? Definitely. Ground truth data always on a utmost requirements when for a model validation. Because even for the remote sensing, even for the crop growth model, even for the simulation model, if you have the actual crop yield, then only you can say validate or parameterize your you can say parameterize the equations and validate your results, as well as you can say make a comparison. Even if you want to go the crop simulation model, the simulation can only be possible if you have the actual ground informations for the same. The next question, can you explain main benefits of the machine learning crop yielding for or our use? Okay, so the main benefits of the machine learning is that like rather than using a traditional approach in machine learning, as you integrate a large volume of data sets, basically we call it a big data cube. So as you are working on the larger data sets, you may get the your you can say statistical or you can say your machine learning based results in more realistic manner, because when you use larger data sets, the redundancy may reduce, as well as the accuracy may improve. So accuracy only can improve if you have a large volume of data sets in case of machine learning part, because machine learning required large number of data sets, not you can say you can say 50, 70 or 100 number of you can say data sets in the Excel sheet, and you are working with respect to machine learning. It is not so. If you have 1,000 numbers of that's why remote sensing, like where you can say millions of pixel are there, you are working on the number of images, hundreds of images, thousands of images you are working, then machine learning give the more precise with respect to machine learning integration. There is a one questions, can you explain the estimation of parametric index? Okay, parametric index, like as you have NDVI for example, like any satellite derived NDVI, you have satellite derived LST, you have satellite derived precipitation, their product precipitation, soil moisture. If you generate you can say all the these input based index, like NDVI based VCI, temperature based TCI, temperature condition index, vegetation condition index, precipitation condition index, soil moisture condition index, and if you make integration, maybe based on the MCDM, multi criteria decision making, maybe fuzzy logic approach or maybe weighing based approach, if you integrate and generate a combined index, and that is with a scaled part, so that's define a parametric index. So you knew index integration with the more than two type of you can say spectral indices or the satellite derived products. Okay, this is a question, what are the emerging trends and future direction in advanced data analytics for crop yield estimation, considering advancement in AI, edge computing and new sensor technology? Okay, so basically as we discussed, like as also government of India and their officials are working in the Yes Strength program, where there are different 5 type of models that they are using. They are basically like using a big data and also advanced technology like AIML part also, parametric test also, semi-empirical model also. So these all sort of you can say modeling approach basically give the answer with respect to advanced data analytics part. and as much as longer period you have data sets with respect to the field by field variability on the on ground informations, that may, you can say, serve the purpose for the same. Okay, one participant asked, what is the Prozel RTM? Prozel basically they are a some of the, you can say, CRTM, canopy radiative transfer model. RTM is the radiative transfer model is there. Prozel is the integration of the prospect and cell model. Basically, where you integrate some of the crop and soil basis information and simulate the conditions in, you can say, inverse modeling approach. So that's the very basics about the Prozel RTM model. One question is there, which particular spectral index is more used for building ML model in crop forecast? They are not any defined, like, but you can say research or developer mostly use NDVI index in that which is specific for spectral vegetation index only. I am talking the spectral vegetation index only. For, as if you integrate that thermal, then they integrate that LST. If you air temperature based, or you can say temperature based index, then there the GDD, you can say growing degree day. So likewise, based on, you can say, what kind of input or scaled parameter you want to introduce in your equations, based on that you may select the particular index only. There is a question, how to integrate diverse multi-dimensional data sets like weather data, soil data, satellite imagery into ML model that can accurately predict crop yield, especially for uncertainty cases. Okay, you are asking a complete blend of all the techniques in one go. Definitely, like, as people, some of the researchers are working on the same, but there are, you can say, very limited studies are there where they integrate the crop models like all, you know, crop, soil management, weather parameters with respect to remote sensing. But the important part is there, like their accuracy, as well as where you can encounter field to field variability and also simulation in terms of yield forecasting. That's the important thing. And there are, you can say, certain limitations also with respect to the data processing part, data integration, be more especially if I am saying the data assimilation part also in the same. So this is all from my side. As I just saw in the chat box, number of queries are, you can say, raised by number of participants. So thank you very much each and every participants, listener, those who put their keen interest in this particular lecture. Thank you from my side.